Welcome to episode 4 of Garden Mechanics. This week we're going to be looking at some more connected particles, looking at lift problems and connected particles on a horizontal plane. We're also going to start to look at friction, which is a big one. At the book, it's actually the same exercises as last week, 10E, 10F and Mixed Exercise 10, and that's all out of book 1. Okay, there'll be some book 2 content as well, but I'll give you the questions for that. So it takes a certain type of person to watch a film and think, the mechanics in this, the physics doesn't really look right. Instead of just sitting and enjoying a film like a normal person, some of us, myself not included, like to actually look and see whether the mechanics works, whether it makes sense in the real world, and whether you can analyze it. So that's exactly what we're going to do as a starter task. I've selected 3 clips from films of different genres, and we're going to see whether the mechanics is possible, and we're going to see whether we can analyze it in a bit of detail. So in films, studios will either use special effects or green screens in order to make things possible, or sometimes they actually do these stunts and do these things in real life. For example, in the film The Fast and the Furious 7, which no one's seen, there's a scene in which cars are dropped out of a plane and deploy parachutes and land safely on the ground, which seems pretty ridiculous, but actually they did it, which is amazing. So they actually did this, and that would have required a huge amount of planning and probably a fair bit of mechanics. So the first clip I want you to analyse is from a film called The Peanut Butter Falcon, which is one of Shia LaBeouf's movies, but there's a clip here, I want you to watch it, think about it very carefully. So, is it realistic? Does it make sense? Does it look right? Is it mechanically sound? Clip 2 is from an absolute classic. This is from Homeward Bound, where a cougar is chasing Chance and Shadow, and they come up with a devious plan to thwart said cougar. Almost. Now. This is just classic Chance. So, just to recap, they found a seesaw, and Chance, while shouting 90s references, jumped off onto it and sent the cougar into orbit. Let's have a think about it. So if that clip was, full bore adrenaline, this clip should calm you down a little bit. So this is from a film called Hobbs and Shaw, and in this scene there's a car which is attached to a helicopter by a chain, and if I'm being completely honest, I have no idea what's going on here, but there is some quite interesting things to look at. So, watch this bit in particular. Thinking about our connected particles, I want you to tell me whether this is realistic or not. Okay, so for the 3 clips, I want you to think about them mechanically, decide whether they're possible, decide what rules are being broken or not broken, and make a sort of reasoned response to each one. So the first thing to look at today is lift problems. So if you imagine you're standing in a lift and you're at the bottom of the building and you're about to go up, the first thing you feel is you feel a little bit heavier to start with. So when you accelerate upwards, the floor of the lift is actually pushing you up more than you're pushing it back down, and that's why you go up. That's also why you feel heavy. So your mass hasn't changed, but the force exerted on you by the floor has. So you're going to feel like you're pushing more into the floor. You're going to feel like you're heavier than you are normally. When you're at the top and you go down really quickly, you get the opposite feeling. You feel a bit lighter. It's the same as when you go over a bump in a car. You feel unweighted, and that's because there's less force, there's less normal force acting from the floor of the lift on you. So by that, you feel lighter. Okay, but after a few milliseconds or half a second, you feel your same weight again. You feel normal again. And that's because after the initial acceleration, you go at a constant speed. So after the initial acceleration upwards or the initial acceleration downwards, after a very short amount of time, you go to a constant speed, and so you feel the same. The force upwards from the floor is the same as your weight.
So here is my lift setup. I have, this is my lift floor here. I have a set of scales to show the normal reaction force, a little camera that's going to film this dial. I have my 1.25 kilogram mass, which represents the person standing in the lift. And then as I go up, I go to my pulley, and that's just tied up for the moment, but this will pull down. Now this is here to represent a lift, as you'd find in a building, and we're going to accelerate this up and down and see what happens to this normal force on the scales here. Okay, so at the moment we're at rest and the scale is showing 1.25 kilograms, which is the mass of the particle. Okay, we're going to accelerate the lift upwards and see what happens.
So in this first example, when we accelerate our lift upwards, our A goes in this direction. And when we look at the scales, we read off about 2.25 kilograms, roughly. Okay, so we can use that figure in order to work out what the acceleration of the whole system is. If we think about our point here, our mass at the bottom of our lift, its force down all the time must be 1.25 g. Okay, that can't change. That's just the weight of this particle. But we're being told by the scales that it's actually going up with a force of 2.25 g. Okay, I know this is in kilograms, but kilogram scales are actually force scales. So it's 2.25 g going this way. The acceleration is in this direction. So if we use F equals ma, just concentrating on this particle, we have 2.25 g going up minus the 1.25 g going down, and that equals 1.25 a. Okay, so in this case, we end up with just g on this side divided by 1.25, and that gives me an acceleration of 7.84 meters per second. So we just focus here at this point and we see what forces are doing what. This 2.25 g force is making it go up, and the weight of it is 1.25 g down. Now we're going to start at rest at the top, and we're going to allow it to fall. Okay, so in this second situation, when we are accelerating downwards, the minimum force on this particle is 0 kilograms. Okay, on the scale it reads 0 kilograms, so there's 0 force. And so if we draw a particle again, we know we have a weight down of 1.25 g, and at this point when it's accelerating, the force upwards is 0. Okay, so using F equals ma again, resolve downwards, 1.25 g minus 0 equals 1.25 times by the acceleration. So in this case, the acceleration is 1.25 g divided by 1.25. So the acceleration downwards is g meters per second to the minus 2. So what I've actually done in this scenario is I have achieved sort of free fall. Okay, so I've let it accelerate downwards at the rate of gravity. Okay, but you can work out what that rate is by considering this red point here and what the forces are at the base of the lift. The last thing I want to show you is what constant speed looks like. So if we have constant speed in our lift, we shouldn't find that there's any change in the normal reaction force. So I'm going to do this as carefully as I can.
So we're going to go for a constant speed up. Okay, and then a constant speed down.
So for this last example, where we have constant speed, there should be no acceleration. And if we look at the scales, it says 1.25 kilograms. So let's just have a look at this as the last example and sort of make sure we know what we're talking about. The weight down again is 1.25 G. We know from the scales, the force, the normal force on the base of the lift is 1.25 G. Therefore, we have 1.25 G minus 1.25 G equals 1.25 A. So we have 0 equals 1.25 A. Therefore, the acceleration equals 0. Okay, so at this point at the base of the lift, we have equilibrium. Okay, so in this situation, I have a lift and I have a person in the lift who weighs 70 kilograms, and I'm going to give you the tension, and then we're going to work out the acceleration and the normal reaction force. Okay, so the information we need is that this lift weighs 500 kilograms. This is the normal reaction force here, okay, on this person. Here's the tension, and we'll work out the acceleration. Okay, so if we start over here, I'm going to tell you that the tension is 12,000 newtons upwards. Okay, now feel free to pause the video and have a go at finding the acceleration, but I'm just going to crack on with the solution. So what we do is we consider the whole particle. Now the whole particle is going to have a mass of 570 kilograms, which is a weight of 570 G. Okay, so T is moved going upwards, 570 G downwards. So we can kind of roughly see that 12,000 is going to be bigger than 570 times about 10. So we can do 12,000 minus 570 G, and that's going to equal 570 A. Okay, so let's work out, let's bring it to my calculator quickly. Okay, so we get a value of 6,414 newtons, that's the difference. So if I divide that by the mass of the whole system, I get 11.25, let's go for 11.3 ms to the minus 2. Okay, so it's accelerating upwards, 11.3. Okay, so we found the acceleration. So to find the reaction normal, let's just look at the base of the lift and our plucky lift rider. So the person in the lift has a mass of 70, which means they have a weight of 70 G. The reaction from the floor of the lift must be greater than 70 G because they're moving upwards, and we know that they're moving upwards 11.3 ms to the minus 2. So to work out this reaction normal, we do Rn minus 70 G equals 70 A. Okay, so Rn equals, now notice how I'm adding the weight to the accelerated mass because it's going to be more than normal body weight. Okay, so 70 G plus 70 A gives me a force of 1,477 newtons. Okay, that's all good and well, but what does that actually mean that this person's going to feel like? Well, what we can do is we can kind of work out an effective sort of mass. We can say that their mass feels like 1477 divided by 9.8. So usually they weigh, they have a mass of 70, and that's what they're used to. But in this, their sort of effective mass, or what they feel like, is 150.7 kilograms. So what you could say is it feels like they're just over twice their normal mass. Okay, right, let's move over to this side. We're going to say that instead of having a tension of 12,000, we're going to have a tension of 3,000. So straight away we know it's going to be going in the other direction. Draw the overall diagram again to start with. So we have 570 kilograms in here, tension going upwards, which is 3,000, and the weight going downwards, which is 570 g. We want to work out what its acceleration is. Now we know that 570 g is going to be bigger than 3,000 because 570 times 10 is 5,700. So we write 570 g minus 3,000, and that equals 570 A. So the resultant force is going to be 2,586. Okay, if we divide that by 570, we get the acceleration, which is 4.53. So let's go for 4.5. That sounds pretty good. Okay, and that acceleration is downwards. Okay, so we get the acceleration is positive, but we know this one's going downwards. Okay, so essentially what this 3,000 newtons is doing is it's reducing the acceleration from 9.8 down to 4.5. Okay, so the reaction, again, base of the lift, our daredevil lift rider here, Rn this way, their weight 70g this way, and we know that the acceleration is 4.5. So in this case we're going downwards, so it's 70g subtract Rn equals 70A. So in this case, our Rn is going to be 70g subtract this acceleration downwards. So away from the normal weight, we're taking away this accelerated mass. On this side, on the left-hand side, we added it because it means we're going to have more weight down. But on this side, we take it away because there's going to be less. Okay, and this gives me a reaction normal of 371 newtons. Again, what's this going to feel like? Well, let's divide it by 9.8. And you are going to feel, if this happens, like your mass is only 37.9 kilograms. Okay, this is a sort of basic example of a lift problem. But again, just like we connect to particles, we look at the whole system first, then we zoom in on the smaller part to work out what the reaction normal is.
Here's a question out of the textbook for you to look at. Have a read, and I'll show you how to do it.
Okay, so particle A has a mass of 110, particle B has a mass of 190. The whole lift weighs 1,700 kilograms and it is descending this way at 1.8 meters per second to the minus 2. Okay, so the acceleration is downwards, and the first thing is to find the tension in the cable. Okay, so first things first, we're going to model this as one combined mass. So you have 1,700 plus 110 plus 190, which gives us a convenient number of 2,000 kilograms. So we have 2,000 G as our force downwards, T is our force upwards, and the acceleration is 1.8 downwards. Okay, so we know that 2,000 G must be more than T, so we're going to write 2,000 G minus T equals 2,000 multiplied by 1.8. Okay, positive 1.8 because we're saying that downwards is positive in this situation. Okay, so therefore T is going to equal 2,000 G subtract 2,000 multiplied by 1.8. And that gives me a value of 16,000 newtons. Okay, so the less tension in this situation, the faster it's going to accelerate. If there was no tension, it would accelerate at 9.8 meters per second. Okay, so that's A done. The force exerted on box B by box A. Okay, well, let's have a look. So the normal force from box B on box A is what we're looking for. So we have our level here, which we'll call box B. We have 110 kilograms, which is box A. This is the normal reaction force. We have 110 kilograms times G down, so 110 G downwards is the weight. We have Rn going upwards, and remember we're accelerating in this direction at 1.8. Okay, so just looking at this situation, we can write this as 110 G minus Rn equals 110 multiplied by 1.8. Notice how it's very similar to what I did in the first place, but just focusing on this particle here as opposed to the whole system. Okay, and this gives me a reaction of 880 newtons. Okay, so the floor of the lift, so the reaction from the floor of the lift, so here, this one, I'll just go over here for this. If this is the floor of the lift, then I combine the two masses above it. Okay, so the two masses above add together to make 300. So downwards I have 300 G. The reaction normal is this way, Rn, and again I'm going this way at 1.8. So exactly the same process. 300 G must be bigger than Rn, so it's 300 minus Rn equals 300 multiplied by 1.8. Okay, so the reaction on the floor of the lift is 2,400 newtons. Okay, so notice how in each part of the question it's basically the same method. The only difference is, to start with, I look at the whole thing, so I look at the whole system. Second question, just look at A, and then the third question, I just look at A and B. Task 1 is all about lift problems, so get stuck in. Have a go. Okay, so for the next connected particle setup, we have a horizontal plane and a particle on top which I'm modelling as frictionless. This is attached to a cable which runs over a frictionless pulley, and below that is a weight hanging vertically. I'm going to release this particle from rest and watch as it accelerates. So before we see what happens, let's look at the maths behind it. Okay, so if we set this problem up, we have our 2.5 kilogram particle here and we have our 0.3 kilogram particle here. Remember, in here there is no friction, so you need to worry about that for the moment. Now, for connected particles, we're going to do the same method as we've done before. So we're going to look at each individual particle and come up with an equation for it, and then combine them. So for this particle here, I have my tension going upwards, and I have my 2.5 G going downwards. Okay, so for this particle, we know it's going to go this way. We know this one's going to drop. So we have 2.5 kilograms, sorry, 2.5 G minus T, and that equals 2.5 A. Okay, that's our first equation. So our second equation, if we look at this particle, I have my block here, and in this direction is T. We have no resistive force going this way. So for this one, we can draw an equation which is that T minus nothing equals 0.3 A. So T equals 0.3 A. Now, if I combine these two equations, then if I add them together, I end up with 2.5 G equals 2.8 A. So if I divide 2.5 G by 2.8, I get an acceleration value of 8.75. Okay, so my acceleration is 8.75. So what's the tension in the cable? Well, let's use this second equation here. T equals 0.3 A. So I can do T equals 0.3 multiplied by 8.75. If I work this through, I get 2.625 newtons. Okay, so the method I've done, very similar to other connected particles questions. I focused on this particle, worked out an equation, and then I focused on this particle and worked out an equation.
3, 2, 1.
So in the first stage, after releasing it, our particle accelerates along as the weight descends. There is some tension in the cable because the system is accelerating, and they're both accelerating at the same rate. Now, as soon as that mass hits the ground, the tension is going to disappear. And as you can see, the cable becomes completely slack and the acceleration has been removed. Okay, so before we bring friction into play, let's have a go at some of these connected particle problems without friction. Have a go at task 2. So before we get into the idea of friction, we need to fully understand the variability and acceleration due to mass. Now, it's a bit of a misnomer. You might think that because there's no friction, the mass doesn't matter, but the mass does matter because of inertia. We're trying to move a mass using a force. So in the example we just looked at, let's keep the 2.5 kilogram driving force, sort of driving weight, the same. But let's see what happens when we change the mass m here. Now, if I write an equation, as I already have, of 2.5 G minus T equals 2.5 A, and I write my second equation for my second particle, which remember we wrote as T equals, well, last time it was 0.3 A, but now it's MA. If I combine these equations, I end up with 2.5 G equals 2.5 plus the mass of my second particle times by the acceleration. So this gives me a formula for my acceleration of the driving force divided by the total mass. Okay, so this is important. And with this in mind, the tension is then dictated by timesing m by this acceleration. So what we're going to do is we're going to go and have a look in Excel, and we're going to see what happens as we change m. Okay, so here on Excel, I've got the point we've already worked out previously. When it was the 0.3 kilograms, we found that we had 8.75 meters per second, and that's plotted here. Now the question is, as I change m, as I change the mass, what's going to happen to my acceleration and what's going to happen to the tension? We should understand that as the mass increases, the acceleration is going to reduce, which seems to be what happens, and the tension is going to increase. Now, just to show you the formula here, I've just done in here exactly what we've just written down. I've got the mass of the first particle times by gravity divided by the combined masses. Okay, so if I extend these graph areas on, it looks linear. Okay, something's happening. Okay, if I take this all the way down, okay, up to, it's arbitrary, but 42.5 kilograms. Let's have a look. Okay. So what we have, and if you look at the equation carefully, maybe you should expect it, we have a reciprocal graph. So as you increase the mass in a frictionless situation, as you increase it, the acceleration reduces, but it looks like it's never going to reach zero. Okay, and that should make a little bit of sense. If it's frictionless, we have to think about both ends of this graph and whether they are applicable. If there's zero mass, we have an almost infinite acceleration. So that's also something to think about. So the two ends of this graph, because a frictionless situation is very difficult to actually achieve, the two ends of this graph are a little bit debatable. But in between, you can see we have this reciprocal relationship. The more mass you have, the less acceleration you have, and it decays down to sort of nearly zero. And if I plot both the tension and the acceleration, what we find is the acceleration decreases and the tension increases up to a maximum line. Now this maximum line here, if you may be able to work out what this line is, well, this line must be 24.5 newtons, because that is 2.5 kilograms times by gravity. So this upper level here must be 24.5. Okay? So the tension as a maximum will be the weight of the first particle. First setup was a frictionless particle, and I'll show you what I've done. I've taken, highly scientific, I've taken the wheels off and I've turned the particle upside down. So what I've got now is the surface on the table is this surface here. Okay, we're going to put the same mass on the end, and we're going to see what happens when I increase the mass of this particle. As you can see, in each subsequent test, I'm increasing the mass on this particle. So the mass is changing, but the contact between the particle and the table is staying exactly the same. The driving force from the first particle is also the same. And here they are side by side with the masses labelled on. So when you let them go, you can see there's a vast difference between the acceleration of the lighter particles and the heavier ones. What I've done is I have recorded the times for the particles to travel 56 centimetres from rest. Okay, so we took these values, the time it took for each particle to travel 56 centimetres, and we've input those values into this column here, into the time column. And what I've done is I've used the suva s equals ut plus half at squared, rearranged it, and used that to work out my acceleration. And I've put them in here. Now, when I plot these, the red line here is my non-friction situation. So this has been calculated just like we did on the first Excel spreadsheet. So this is my sort of reciprocal graph, which is going down towards zero. And green here is my actual data from the friction situation. So I'm pleased to report that they look quite similar. This last one, as you know, it never actually reached 56 centimetres, so it's down here at zero. But you can hopefully see they've got the same kind of line. So what this means is that there's something some coefficient or some value which is changing between these two graphs. The red one's frictionless, and there's something which is driving it down, which is reducing the acceleration. And that's the friction, but it's not the mass. So there's something independent to the mass which is causing the reduction in acceleration. And this is called mu. So mu is our friction coefficient, and it's nothing to do with force. It is all to do with the materials and the surface interaction. Mu is a value between 0 and 1. A value of 0 is completely frictionless or smooth. We've looked at that kind of thing so far. And a value of 1 means completely fixed in place. It won't move at all. Okay, so to explore the idea of friction coefficient, I'm going to use these two trays, which are the same mass and have the same shape at the bottom. Now, inside these, I'm going to place 2.5 kilograms so that they have exactly the same mass, so I've accounted for that variable. Now, what I'm going to place underneath these, one of these 4 mediums, and we're going to see which one has the least friction. Okay, I'm going to do this by placing it at the end of this table and then tilting the table until one of them moves. Okay, so under this one is a glossy magazine, and under this one is our control, so nothing. And what I'm going to do is each time the one that has the least friction is going to get knocked out until we find which has the most friction. Okay, so this time just a sheet of paper. Okay, so just the paper. I think the paper's just you're out. A tea towel. Whoa! Tesco magazine, just. Okay, so the last one we've got is, and this is, you know, definitely the favourite. This is sort of a rubberized resistance band thing, isn't it, I suppose. So, let's have a look. Okay, so the tablecloth is out. So our winner is this one. Okay, so here is your winner, and as we go this way, the coefficient of friction reduces. So the friction, Fr, is defined by the coefficient of friction, which is a number between 0 and 1, which is also with the surface interaction between your particle and the plane. So the mu is set. So to increase the friction, I would have to increase R. Now R is the force going down here, which comes back up from the table as a normal force. Okay, so to increase the R, I can increase the mass. So if I have more mass, there's going to be more friction when I move it, because I'm doing the coefficient of friction times by this force here, the reaction normal. Okay? So the coefficient of friction stays the same, but as I increase the mass, I increase the force down, therefore I increase the overall friction. So here it is, the equation for friction. The frictional force equals the coefficient of friction multiplied by the normal reaction force. So if either the coefficient of friction increases or the normal reaction force increases, the overall frictional force goes up. We can demonstrate the idea of a normal force on a surface using, this is why you're not my videos, using 2 people and a book. So if you place this book between you, and I want you to hold it as lightly as you can so it doesn't move. Okay, so as lightly. So when they're holding it really, really lightly, I can really quickly take it out because there's very little friction. Now the coefficient of friction is the same, but they're not applying much force to it. Now I want you to put all your weight into it. There we go. Try and stay still. There we go. So now, it's really difficult for me to pull this book out of their grip. Good book as well. Because of the extra force being placed on it.
You've got a massive bug in your head. Stay still.
Oh, check it out. That's not really how the camera works.
Is it not?
What is it? What type of bug is it? I'm not going to edit this at all. What type of bug is it? Wait, where is
No,
it?
it's on your stomach. It's on your stomach.
Okay, so I'm not entirely sure how useful that was, but hopefully you got the point that if you increase this normal force, you increase the friction. And this happens whilst the coefficient of friction, or mu, stays the same. Okay, so let's go through a fairly basic friction question, but one which will form the basis of being able to work out friction for other situations. So I've got a 5 kilogram block here. I'm told that the coefficient of friction is 0.4. And I've got a driving force of 50 newtons. So I want to work out what the resultant force is and what the acceleration is of this particle. So the first thing I'm going to do is I'm going to draw the weight of this block down, which is 5g. Now the weight of the block down is 5g, therefore the reaction normal, or Rn, must equal 5g. Okay, because there's no other forces acting, so the reaction normal is 5g. Now the next thing I'm going to do is I'm going to work out this frictional force. So my Fr is going to equal 0.4 times by my reaction normal, which is 5g. If I work this through, I get a value of 19.6 newtons. Now this is the maximum frictional force that can occur in this situation. Okay, so this block being 5 kilograms and having a coefficient of friction of 0.4, it has a maximum friction of 19.6. So to work out the resultant force, I'm going to do 50 minus Fr. So Fr is going to act in the opposite direction to the motion. This is because friction is a passive force. It doesn't act on its own. It just it works against other forces. So 50 newtons is this way. Therefore, the friction goes left. So I have 50 minus my frictional force, and that equals 5 times A. So I have 50 minus 19.6. And that gives me an acceleration of 6.08 ms to the minus 2. Okay, the resultant force is 30.4. Okay, so it's going to move to the right, it's going to accelerate at 6.08 because the frictional force works against the 50. Okay, so Fr is the maximum. Okay, so the other thing to think about is if this wasn't 50 newtons, if this was less than 19.6, this wouldn't move. Okay, it's got to overcome this frictional force of 19.6 before it moves. So if this is less than 19.6, it's not going to move at all. Okay, if it's 19.6 exactly, we'll have an equilibrium situation. Okay, so there's going to be a lot more questions to have a go at, and there's some on task 3 to get used to this idea of using Fr equals mu Rn. Okay, so here we have a 20 kilogram particle, and that's attached via a pulley to an 8 kilogram particle, which is on a horizontal plane. We're told that the coefficient of friction is 1/5, so let's make a start. So let's label on our tensions to start with. And I'm also going to label on here Fr, okay, my frictional force. Down here I've got the weight of the first particle, which is 20g. And here I have the weight of my second particle, which is 8g. Therefore, my reaction normal force up here is 8g. And I've labelled on everything I need. Okay, so the first thing to do is work out what this value Fr is. So we know that the coefficient of friction is 1/5, so it's going to be 1/5 multiplied by 8g. This gives me a value for FR of 1.6 G. Now I'm going to go back to my connected particles method. I'm going to draw an equation for this first particle, and this is going to be 20G minus T equals 20A. And for my second particle, I have T going to the left. The force to the right is FR, which I know from here is 1.6 G. And this equals 8A. Okay, if I combine these two equations, add them together, I get 18.4 G on this side because the T's have cancelled, and that equals 28A. If I do 18.4 G divided by 28, I get an answer of 6.44 ms to the minus 2. The tension in the cable, I'm going to rearrange this second equation. So I have T equals 8A plus 1.6 G. I do 8 times 6.44 plus 1.6 G. Notice that the frictional force increases the tension here because I've added it on. If I work this through, I get to a T value of 67.2 newtons. If we treat this example here like we did earlier, having a particle of m kilograms with a mass of 2.5 kilograms as our first particle, and we see how the acceleration varies and write an equation, we can start off by writing our two equations for each particle. 2.5 G minus T equals 2.5 A, and T minus mu mg equals ma. If we rearrange these, combine them and rearrange for A, we get this equation here of 24.5 minus 9.8 mu m over the whole mass of the system, which is 2.5 plus m. Now we can use this as a sort of new general equation to compare to our previous example where we did not have friction. Okay, so here are our here's our frictionless data, the 5 points that we've chosen. And if I plot on the reciprocal graph that we modelled it with, it's here. If I then put on my recorded data from my setup with friction, I have my 5 points here. Now, we've rearranged it, the acceleration to this equation. Now, I've used a u instead of a mu because there wasn't a mu on Desmos, but it doesn't really matter. So this mu value is here. Now, what we're going to do is, using this rearranged equation for acceleration, I'm going to adjust this value and see if I can get it to fit our data. So this value of u, if I drag it down, it's not going to be perfect, but somewhere in here. Okay, so I'm going to change the increments that I go up in just to see if I can get it really accurate. It's not really worked, is it? Let's go to 0.3 because I think it's between 0.2 and 0.3. So it's looking, I would say, as a best bet somewhere about there. Okay, so from this and from our data, although it's limited, we can find that the best fit in our model is that mu has a value of 1/4 or 0.25. Okay, let's combine this all together. We're going to combine our connected particles with our new knowledge of F equals mu r. Okay, our 3 films, our challenge question. Let's get straight into it. So this first one, we have a man firing a shotgun, and he is thrown backwards maybe 2 or 3 meters. And this is what it should look like in real life. Not overly dramatic. In the film, a couple of weird things happen. The first thing is the gun drops straight down, and the person firing it gets thrown backwards about 3 meters. Hopefully I'm going to be able to describe to you this completely breaks the laws of physics. Here are a few notes I made. So a shotgun works by having an explosion. This fires a mass out the front of the gun at an acceleration. Not a lot of mass, but very, very fast. Because of Newton's third law, there must be a recoil force, which is exactly the same. Now, to counteract this, you brace the gun, and it will jam into your shoulder quite hard, but it definitely will not throw you backwards. In fact, a quick Google brings up the highly reliable physics forum source, and it says that we have about 30 newtons of force. Now, 30 newtons of force is not going to pick up a grown man and throw them backwards 3 meters. So this is, I'm afraid to say, total nonsense. And the main problem I have with it is actually what happens to the gun. The gun, for some reason, stays in the same place. What on earth is making the person firing it fly backwards? So, load of rubbish. That stuck out to me when I saw the trailer. Yeah, just chaos. And hopefully you notice yourself that this is ridiculous. Okay, so to Homeward Bound, where Chance and Shadow are trying to outwit a cougar. The first thing I'll tell you about this is that the mass of a cougar, on average, is about 68 kilograms. And the mass of an American bulldog is about 50 kilograms. So, let's have a look. Our dog, I know this drawing is incredible. You don't need to tell me, I already know. So the dog's going to jump off a platform, which I'm going to say is 5 meters. I think that's an overestimate. But let's give Chance a chance. He's going to jump off and land with such a velocity that our heavier particle is going to fly up and over him into the ravine below. So the maths behind this, well, if you look at it using SUVATs, if we ignore their masses to start with, then we know if Chance jumps from 5 meters, his velocity when he hits the platform is going to be 10 meters per second. And so as a result, the highest the cougar can reach is the same height that Chance jumped from, so 5 meters. So that's that. Here's an example of that in action. Acrobats do this. It's called the wibbly wobbly jump board of death, and they jump back up to the same height the other one came from. You can see. Now, the other thing is they jump straight up, so the cougar's trajectory is not going to be this big parabola, this big arc that we're expecting. And if you want to take it even further, thinking about momentum, which is a GCSE concept in physics, the momentum that the dog is going to give the seesaw is going to have to be divided by the larger mass of the cougar. So actually, more realistically, the cougar is going to reach about 2.75 meters instead. So what's actually going to happen, and this is going to ruin the film, is Chance is going to jump, the cougar's going to go up a little bit, come back down, be extremely annoyed about it, and that'll be the end of the film. So yeah, this is nonsense. Sorry, Chance, but it's curtains, mate. Okay, we're nearly there. Our last one, Hobbs and Shaw. So they are towing a helicopter behind them, and all sorts of nonsense is going on. Cars are flipping and exploding. Cliffs are falling away. It's just a standard Jason Statham day out. So we have a situation here where our character, Hobbs, I guess, is holding the helicopter. This is the first situation to think about. He's holding the helicopter, so he's taking the tension between these two connected particles. So this is the one to think about. Is this realistic? Is this possible? Well, the question actually isn't, is he strong enough? The question is, how is the car staying on the ground? Because helicopters can lift cars, and even if this one can't lift this car, it could at least unweight it. And if it unweights it enough, it's not going to have any friction. It's not going to have a kind of normal force downwards into the ground, so it won't be able to drive along. So this part, will it be able to hold that tension in the cable? Probably not. But the bigger problem I have with this, and hopefully you have as well, is that this car is not going to be able to stay on the ground or drive properly with a helicopter providing that much upthrust. So if we sort of delude ourselves into thinking that this could be a situation which occurs, this next bit actually isn't too bad. What happens is the car slows and turns and skids, and in doing this we can see that the cable goes slack, so there's now no tension in the cable. At this point our character has time to reattach the cable to this big drum, and they're back in business towing along a helicopter in their car. So actually that bit isn't too bad. By decelerating the first particle, you are reducing all the tension in the cable connecting them, and that means you then have the ability to wind this back on. So actually that bit, pretty good. I quite like that. So as much as this seems like I'm trying to ruin films, and I am, it's really important that you don't sort of forget that everything we do has a real world application, and you're going to be able to see it everywhere around you, and hopefully when things don't work or when things look wrong, you'll be able to explain them using your knowledge of mechanics. Okay, so, you know, stay aware of mechanics and have a think. Next week, we're going to be looking at inclined planes, which is a big one. So, yeah, got that to look forward to. Right, enjoy this one. Any problems, let me know. And there are also solution videos to the tasks on the channel. Okay, have fun.